Hello there, folks. Welcome back to Learn Synthesis with VCV Rack. I'm Dr. Lawrence W. Moore, your host. And in this episode, we are going to focus on two things. The first thing is the four basic wave shapes: sine, triangle, sawtooth, and pulse wave family. Also, the square wave, which is a member of that family and the primary one in that family. And then I'm also going to show you something I came across in making your monophonic, that's what we've been doing so far, monophonic synth sound a little bit smoother. I stumbled across that and thought I'd put it in this episode. So away we go. Okay, so here we are. Now this is basically the standard setup I've been using, except I have the Wavetable VCO in here instead of our usual VCO. I decided to use this because it actually shows the wave shapes that you're using, and I think that would be a good visual thing as an example of what I'm talking about when I talk about the four basic waveforms. But before we get to that, I just want to show you something. You notice how last time I decided to take a velocity from our MIDI to CV in and put it into the VCA here to control it. That way our velocity governs the level, the peak level of our attack in the envelope when it comes in. So you get more of a dynamic response, like soft sounds and louder sounds. You get more variation that way. But, and I didn't really notice it so much last time, but especially with the Wavetable VCO here, like if you do a glissando where you're basically playing multiple notes in a row, but not letting the individual notes release, notice how you hear some snaps in between the notes. Those are called artifacts. And basically, you can see here in the VCA where the velocity is controlling the level, the output level from our VCO. Right here, you see it fluctuates. Those are sudden changes in amplitude, basically. And the envelope can't really do much about it because when you play other notes while holding the previous note, it stays here in the sustain portion of the envelope. So what's happening is basically fluctuating levels of amplitude are going through, and in digital synthesis, that results in a snapping sound called an artifact. There is a way to fix that. And any of you that saw my series Learn Synthesis with Pure Data, series 1 or 2, I always control that with basically line tilde, an object that basically goes from one level of amplitude to the next one over a designated amount of time, basically drawing a line in between them. And that line segment can be really short in a time interval, like hardly noticeable to the human ear, like 25 milliseconds even, which is nothing time-wise to us. But it smooths it out enough that the numbers, which are the sample numbers in digital synthesis, basically move to each other gradually enough that you don't hear the artifact. Now, this is still digital synthesis. It's modeling analog synthesis, but it's still digital, so you get that artifact. Well, there's a way around that. And so what I'm going to do is shift click these modules here and move them over. And then I'm going to right click here, and I'm going to call up a module called process. This is a module that, if you follow my recommendation in episode 1, I believe. Yeah, it was episode 1. Oh, this is the wrong one. That's logic. Close, but not quite. Here we go. Process. If you followed what I suggested in episode 1, you would have downloaded all of the VCV brand of modules that are free, and this would have definitely come with it. So anyway, this has the ability to give us what we're looking for, a transition from level to level. Now this deals with CV signals, so it's in here is CV signals, and our velocity is a CV signal, so we're going to bring our velocity in here, and then we're going to come out the glide outlet here. This basically gives us a smooth transition from velocity level to velocity level. So our VCA, you may not see it visually that clearly, but basically it will go from level to level to level more smoothly. In order for that to be effective, though, we got to turn up our slew knob here. And I found the 12 o'clock position to be good for this. So now, whoops, I still heard some. Hold on. We are coming out glide here. Oh, I know what I forgot. We're not triggering it with the gate. Basically, this executes its functions when you have a signal coming to its gate. So we go from destination to source here. So the gate for each note, when notes go on and off, it triggers this. And it basically processes a glide from the velocity values one to another. There you go. Now, sometimes you can be a little stumbly with how you play and still hear an artifact here and there, but when I'm not bumping extra keys, you know, accidentally, it's fine. When I'm rough with it, you can still hear an artifact, but there we go. So now we got a smooth playing monophonic synth. So that's one of the things I wanted to show you. That's why it's good to watch the episodes beginning to end and in order, so you don't miss some of these useful tidbits that I will come across and point out. So anyway, on to our basic wave shapes. We've normally been using, I'll zoom out here a little bit, this VCO here. Okay, and now this VCV Rack models like analog synthesizer components. And so this is meant to sound like your typical VCO in a Eurorack system. This is meant to model a wavetable VCO. And the difference would be a wavetable is actually a digital approach to synthesis, where this is like a digital wavetable. But in VCV Rack, everything truly is digital because it's software. But the idea is that this is modeling what a wavetable digital synthesizer VCO would sound like as composed to an analog. And in fact, we could kind of compare the sounds here. Let me see here. I'm going to hook up this properly. And what we'll do is hear this one first. And I'll play basically the same notes, but we'll hear this one instead. So what we'll do is disconnect this wavetable VCO and connect the sine out in its place. You hear it's a little bit buzzier, you know, respectively, considering the fact that they are both sine waves and they aren't supposed to be buzzy at all. But you see, there is a difference. And maybe with this one, that might contribute to why I didn't hear the artifacts as much. But now that we have the smoothing going on, it's much better anyway. So anyway, so that's why there are different ones. They will have a slightly different timbre because it is modeling analog components, which are electrically driven. And so there's always going to be a little bit of noise. A pure digital sine wave is going to sound very round and very smooth because sine waves in general are basically a single frequency. The smooth, round, sinusoidal shape indicates that this is a single frequency. So whatever note you're playing, that's the frequency you're hearing. And this definitely sounds cleaner because it's modeling a digital sine wave, where as opposed to an analog sounding sine wave that will actually have trace amounts of other frequencies in it due to the circuitry and the fact that it is not as mathematical, just pure numbers creating this shape like it would be in digital. So VCV Rack is modeling those two different sounds. So in order to get other wave shapes with this VCO, the Wavetable VCO, you use this dial here and you see it's bending the shape. And right about there, we get a triangle wave. And what we're actually hearing in sound-wise is more overtones in the sound. Those are higher frequencies that are at a lower level compared to what we call the fundamental. The fundamental is the pitch that you're hearing. If you're playing A440, I think that's here. That's 440 hertz. On a sine wave, that would be the only frequency in the sound. Oh, I dragged the module instead of the dial. So what you're hearing there is some more higher frequencies added to the sound. Higher frequencies above the fundamental, the pitch that you hear, are called overtones in general. And in this case, they are specific harmonics that make a triangular shape. Harmonics are overtones or frequencies above the fundamental that are whole numbers times the fundamental frequency. In other words, well, in the triangle wave, they're a little bit different, but you would have a harmonic above the fundamental that is 2 times the frequency of the fundamental. So for 440 hertz, that would be 880 hertz or an octave above. Then you have another harmonic that's 3 times the fundamental, which would be 1320 hertz, or an octave plus a natural perfect fifth above the fundamental. And so on. 4 times the fundamental, 5 times the fundamental, 6 times the fundamental, 7 times, and so forth. And the different varying strengths that these harmonics have give you different shapes. Now, the triangle doesn't have as strong of a harmonic presence as some of the other wave shapes that we're going to explore. And each of them has their, oh boy, I keep doing that. Each of them have their own formula for how you work out their strengths. And the frequencies that are these harmonics are actually, if you take them apart, are really sine waves in and of themselves. For the triangle wave, the formula is 1 over the harmonic number squared, and just including the odd number harmonics. So like the third harmonic would be 1 over 3 squared is 1/9. So it would be 1/9 the strength of the fundamental in relationship. And so on as you go up the odd harmonics. Now, if we go further with this, now we're getting much buzzier. And when we get to this point, we're basically getting a sawtooth wave. This is actually an inverse sawtooth wave. A sawtooth wave is normally slants from upwards to down and then back up. But if you shift this over a bit, that's exactly what you get. So it's really a matter of phase or position here. But in any case, for all intents and purposes, it sounds like a sawtooth. It is a sawtooth. So there is our sawtooth sound. Now the sawtooth harmonic formula is 1 over the harmonic number. And that includes the even and odd harmonics. So there is an octave above 880 hertz with a 440 hertz fundamental. There is a harmonic at 880 hertz, which is 2 times the fundamental frequency. And the formula is 1 over 2 is its strength, or basically half the strength, half the presence as the fundamental. So that's pretty strong in terms of harmonics. And then there will be the third harmonic, or 1320 hertz. That would be 1 over 3, or 1/3 the strength. Then the fourth harmonic will be 1/4 the strength. The fifth harmonic 1/5 the strength, and so on. And theoretically it can go up infinitely so, but usually in the digital world there's a limit as to how many harmonics are actually added. It could go up to maybe 24 harmonics or something like that. But if we continue to turn the dial, we're going to actually hear a little less intensity of harmonics. You hear how in the higher frequencies it's a little less buzzy. This is our square wave. And its harmonic formula is 1 over the harmonic number and just the odd harmonics included. So there wouldn't be a second harmonic with 1 over 2 or 1/2 strength. There will be 1 over 3 because the third harmonic's included. 1 over 5, the fifth harmonic's included. And, these fractions are the strengths, and the number is the number of the harmonic. But basically, it is stronger in harmonic presence than the triangle wave because there the strengths are also just the odd harmonics, but they are 1 over the harmonic number squared, which means the fraction, like the third harmonic for a triangle wave, is 1 over 3 squared, or 1 over 9. In the square wave, it's 1 over 3. So 1/3 is larger than 1/9. In other words, so it's a stronger presence for each of the harmonics going upward. Okay, so those are the harmonic formulas. It's kind of good to know. And really, you can theoretically produce all these wave shapes with a bunch of sine wave oscillators, attenuated to the proper strength for the formula of that harmonic strength, and add them all together, mix them all together, and you would, the more harmonics you include, the closer you get to the exact shape of the wave. But, as you add harmonics, you will see bumpiness and stuff like that. And as you add more and more, they get more and more accurate, almost like a higher and higher resolution photograph. So that's how that works, but nobody wants to put out that many sine wave oscillators and stuff, so we have the choice of using this or this. So let's hear the difference here between the square wave on the Wavetable oscillator and the square wave here from this VCO. They sound very close to one another, actually. Let's try the sawtooth here. So I'm going to move this to about the 3 o'clock position. And compare that to, come on, the sawtooth down here. Okay, there is a difference there. There definitely seems to be more of a drive behind the upper harmonics in the wavetable version. Let's hear the triangle wave then. I keep trying to move it to somewhere here because this one has the 4 different wave shapes laid out as different outputs. Here there's one output. Quite subdued in the harmonics, and triangle waves are supposed to be. Let's see if it sounds the same here. A little different, a little less bottom, and a little bit more, I think, in the harmonics, but it's very close. And we already heard the sine wave comparison. You're going to get a little bit of residual upper frequencies from this module because it's imitating like an actual analog module, whereas this one is more pure to the sine wave sound. Okay, so what I'm going to do though is take out this module here and talk a little bit about these. So what can you use a sine wave for? Well, that's a triangle wave. Well, in the next episode, we're going to get into filtering, and we won't be able to do anything with a sine wave as far as the sound producing oscillator is concerned when filtering, because it's one frequency, and you can't tailor any higher frequencies, kind of manipulate its timbre. But there are uses for it. For instance, like in a bass sound, you could definitely use this as like some bottom end. Now I'm going to add another one of these wavetable oscillators. VCO. Helps if you type it. VCO, here we go. Wavetable oscillator. And let's hook it up. Yeah, I should zoom in this way so we don't get that extra mouse cursor appearing. So we're going to hook up the voltage per octave. Put here. And what we're going to do is we're going to combine our sine wave up there with a square wave down here. So the first step is to put this on square wave. And then what I'm going to do is copy these down. Shift click on each one. Let me see here, I didn't get you. And then we can Control C. Then just click down here to tell it this is where we want to paste. Control V to paste. I think it would be Command C and Command V in Mac. Alrighty. Now let's hook it up. Since we copied these modules, they are hooked up with everything that is connected to them. But our output from this VCO needs to go into this VCA here. And then we need to hook up everything as far as the MIDI is concerned, which means the input here is going to be receiving from velocity up here. The gate here is receiving from the gate up there. And then we have our gate over here that triggers the envelope. That also needs to be hooked up to the gate above. Okay. So now, let's make sure I hear both of them. Now, yeah, we have two. I copied the audio. We do things that way. We'll put the audio over here. And in between, we're going to put a mixer to mix the two signal chains. I recommend using, to start, a mixer right here. This also comes with it if you download all the free VCV brand modules like I show you how to do in episode 1. This would come with it. So this is input for channel 1. And we're going to take this VCA and output it as channel 2. They're mixed evenly right now. And then the mix output is here to go into the left mono. There, we're hearing equal parts of sine wave plus square wave. Now, to make this a little more interesting, I'm going to detune the sine wave. And let's reduce our square wave here a little bit. So there, we basically have an octave differentiation, and it sounds pretty good. The sine wave adds a lot of bottom to the square wave. A lot of times square waves can be used as a bass. Let me turn down the sine wave here. And let's just hear the square wave on its own. There, that would be it, and it's a bass. Sounds pretty good, but you can add this sine wave as down the octave as we have it tuned and turn it up here, and you get a little bit more of a wash in the bass there, a nice low. It also gives it more bottom if you're playing it higher. Okay, now let's hear it with another wave shape here. Try the sawtooth, and we'll keep the sine there doing what it's doing. Sounds pretty cool. So there for the sawtooth, it's adding a lot of bottom end as well. Let's put it in this hybrid shape here that's not officially one of the 4 basic wave shapes, but kind of like a in-between shape. This one right here, so you can see it. But this dial gives you lots of in-between. And since we were looking at like useful options for oscillators last time, let's plug it in LFO. and see what happens when we take this LFO. We'll take a sine wave shape as its output and plug that in. I think we can see, this is called wavetable position. You can plug it in here and have it alter the shape, but of course we need to use this to adjust it. If we turn it to the right, it'll be increasing. So let's start at halfway. And now it should be fluctuating between this hybrid shape between a sawtooth and a triangle wave up to a square wave. And you see it visually actually does that. Now, another thing we can do, let's take this out. I'm just going to click on it, delete. Let us take our envelope generator. I think if we copy the same one, we'll get the same shape. So basically, another thing you can do, if you want to copy like the parameters from one module to another, if it has a screen like this, there is an option to go to preset and copy. Now I think it already did that, but just to show you, you can then right click, go to preset and paste if they're the same module type. And now what we're going to do is hook up the gate here to our gate here. So the same shape is going to be executed when you play a note, but this time this is, instead of giving just an amplitude contour to the sound, we're going to have it change wavetable. How about this case? We go inverse direction where it will fluctuate between the sine shape and this hybrid shape here. And all we have to do is take the envelope out and hook it up to position here. Sorry, I was zoomed in with my operating system instead there for a bit. Okay. Aha. When we executed the release, you actually heard a change. Let's have it go the opposite direction, where it starts with a more complex or harmonically present wave shape, and then we can also alter the envelope here, give it a slower attack. Now here the attack is not changing the amplitude of the attack of the sound. It's going to be changing the wave shape here. We can also have that envelope alter its frequency modulation, in other words, changing the frequency of this part of the sound. May sound a little wacky here. Now, when I press notes before releasing the next one, it doesn't do that pitch change because it's staying on the sustained portion of this envelope. But it'll do it for every note where I do attack and release before playing the next note. Oops. Anytime you do that accidentally, just hit Control Z. It'll put it back the way it was. All right, so that's that. So there's a lot of things you can do with this. I haven't been, let's see here. I haven't been working with the sync of these VCOs yet because that's a topic for a whole other episode. That's a subject in and of itself. So I'm going to delete that. Now, we have these two oscillators together. Let us explore what are some other possibilities. For example, take a sawtooth here and a sawtooth here. But now bear in mind, this one is still down an octave from this one. Now, you can also do fine tuning of your pitch shifting. So let's do a little bit of that. On all of these knobs, you can hold down Control and do dragging to get fine tune adjustments. I am not going to be able to do that because I'm holding down a note with the keyboard. There, it's slightly off. And what that's called is chorusing. If we want to get really accurate about it, sorry, I'm going to have to zoom in here so you see the second mouse cursor. But if we right click on this and go to initialize, we'll see what its initial position is in hertz. 261.63. So let's make this 2 hertz up. 263.63. And then let's go down here and do the opposite here. We'll go 2 down, so that would be 259.63. Now what we'll have is an equal amount of distance between these oscillators, meaning 261.63, that frequency is the center point. And you'll kind of perceive that as the pitch because they're equal distance above and below that point. But since they're off from that, they'll sound fatter. They'll sound bigger. That's called chorusing, and it's a great way to fatten up your sound. For example, if we just hear one of these oscillators, sounds like that, but with 2 of them, there we go. A good 1980s sawtooth, buzzy, star brass type of sound. And now what we can do just to be even more funky, right click here, it's still here in the list, take out another oscillator. We're going to go with a 3 oscillator set for fattening things up. And I'm going to have to hook up the volts per octave here to here. We need to copy another set of these. Left click here, Control V to paste. There we go. Now I need to hook this up. Actually it goes here into the VCA. All right, that takes care of the oscillators hookup, but now I gotta hook up to the MIDI. First of all, glide goes to here. Oh, it already is. Yeah, the glide's already hooked up. We just need to hook up the input here to velocity up here. And we need to hook up the gate to the gate up here. And we need to take our final audio output from this VCA here and put it in the mixer. The lower row is the audio inputs. These are control inputs for each channel. So I don't know. No, one more thing I forgot. The gate here. The envelope is not being triggered. So let me hook its gate up here. Let me see. I got to zoom in to make sure I got that right. Apparently I didn't because it's not happening. No. Yeah, this is all right. I think I just missed. It didn't connect. So let's go over here. And we'll do the shifting of an octave here. Hold on. Oh, I was changing the glide. Yeah, that works. Hold on. Are we getting... Oh, yeah, we are on Sine. Let me see if we're hearing it. To turn these two channels down. That's why we're not hearing much of it. Let's see here. Gotta double check everything. Signals going in. Yeah, we're fine on that. The control for this is coming from glide. And the slew is in the 12 o'clock position. That cable mess is going to be hard for me to see. So if I hover over this, now I got to zoom in. So let's zoom out here. Zoom in with the operating system so I can see what it's connected to. The bottom line says from VCV MIDI to CV velocity. Velocity is going in. And this is gate is going in there where it should be. So we're good on that stuff. Going into here. Audio's going in. And the output from here is going to the input of the audio here. The envelope is hooked up here. It is hooked up to gate. Gate output. Yeah, we're good. Something just is not right here. Signal here is looking right. Here. And the output's going into the mixer here. And you're up there as channel 3. Now, one other thing to check here. Oh! That's hooked up to clock. That isn't right. I'm looking for the input here, but is this the right oscillator? All these are hooked up to that input, but this says V oct. Ah, this is Wavetable LFO. It looks the same. All right, just to save ourselves some trouble, let's just copy this one. That was the LFO version of the Wavetable oscillator, because the last thing I added just for fun was a LFO. And so I saw it there, looks the same, and that's what I put in. That's what you do. You trace your signal flow, you trace your steps. And I was hearing, it almost sounds like it's trying to execute a low frequency that we can't hear. And that's exactly what it was doing. Now this is on Sawtooth. Let's put it on Sine. Mix it with the others and tune it down an octave. Actually, I could just right click on each of these and go to initialize, and it goes to its initial value. So they're equal in strength. There we go. So you can make all those types of sounds that you find common in other applications that are using software synths. Well, this is a software synth, but you know, it's designed to give you the look, feel, and model the sound of Eurorack. So you can make those conventional things, and the more you understand the signal flow of what components go into making some sounds, that's how you really learn synthesis and know, all right, if I put this with this and this, I should get a sound kind of like this, and then I could tweak it into shape. And that's a lot of what we'll be doing here as we go along. So I think I covered the 4 basic wave shapes. Next time, we're going to go into filtering, because we could do a lot with this sound, for example, if we did some filtering on it. I'm going to save it. If you found this useful at all, please like, share, subscribe, all those wonderful things that help this channel out. Leave a comment if you have questions or just want to say hello. That's all welcome. All interaction helps the channel and helps me to keep producing these videos. Don't be a stranger. And I do take constructive criticism and anything that helps people learn. So some things I can't fix about me, though. I'm the way I am. All right, so let's zoom out, get a screenshot. Thank you for joining me. I hope you found this useful. And until next time, take care and stay free.